Okay, good morning everybody. Welcome back to the class. Today we have the opportunity to go through two sessions. It's a lot of material, but it's going to go over the weekend, right? So session 18 and 19 are combined and we have a little bit of extra time. Administratively, we have the exam 2. We discussed that last time, but it's here. Exam 2 goes through session 20, which we'll cover on Monday, which is an extension of Mohr Circle, which we're covering today. And so the exam will be on Wednesday, so it's a week from yesterday, and we will have one topic on Tuesday on plane strain with Mohr Circle that won't be on that exam. So if we plan ahead, spend a decent amount of time on this weekend getting through the two sessions that we have, and then if you want to get ahead, you can do the one more and you'll be all set in terms of topics for the exam. Okay. Any questions administratively? Okay. All right. So today we get to continue looking at plane stress. So this is plane stress 2. Okay. And it's an opportunity to discuss principal stresses and max in-plane shear stresses. Okay, so this is session 18. In session 18, there's quite a bit of opportunity to look at what the transformation equations provide. Okay, and you can do a lot of this numerically. So if you go, let's put it this way: we're going to apply the plane stress transformation equations to finding maximum normal stresses, which we call principal stresses, and maximum in-plane shear stresses, which we call maximum in-plane shear stresses. So if we go back the last couple sessions, when we've started to look at combined loadings and the plane stress equations and equilibrium on triangular elements, what do we say the reason we're doing all this was? We said it was because materials fail under different modes. The brittle materials, they often fail kind of in catastrophic failure due to maximum normal stresses. And the ductile materials like the steel, the aluminum that we're typically dealing with, they fail due to maximum shear stresses. Okay, so there's a sliding action on these shear planes. So when we are given a configuration or we're given a state of stress on an element, our goal is to think about what are the dominant shear stresses, what are the dominant normal stresses that can influence whether or not the material is going to fail. And so that's kind of the big point here. And so we're building on what we know about normal stresses, what we know about shear stresses in different types of loading, and then looking at combining them, and then looking at, again, kind of separating or seeing where the maximum shear stresses are occurring and seeing where the maximum normal stresses are occurring. Okay, and so we will get into criteria for failure after this exam number 2 that will say, oh, look, and so I mean, this is a bit of foreshadowing, and it's because, well, this part of the course is quite involved with the math, with the geometries, with the transformations, even with the tensors if you want to do it that way. So we're just trying to keep our view in terms of why all these topics are important. They're very detailed, but they're important because they give us the tools to be able to figure out whether or not a material would fail. Right? So what do you expect on an exam, right? You expect, well, like at least for the final. This exam maybe not so much, but for the final and once we've done failure criteria, it's like, well, will this material yield? Is this material going to fail, right? Is it going to exceed the yield strength that we've talked about, right? So that's why we're trying to understand how we can look at what's happening in a material on a structure relate the structural stresses and strains to the material properties and figure out whether or not we're going to have issues with material failure. Okay, any questions on that? It's kind of the big picture, why we are doing all this work. And you're like, well, once I get out of undergraduate education, I'm just going to use ANSYS, nice t-shirt, or I'm going to use COMSOL, I'm going to use another finite element package, right? And that is true. You will likely do that if you're doing very detailed work, or even if it's not detailed work, but if you need to have some idea of what the safety factors are, you want to be able to figure out what the stresses in the material might be. Okay, and so as these tools have become more and more accessible, right? We did Pre-Pro Max. You use some of the commercial packages like SolidWorks, Inventor, Fusion 360. They actually have the finite element. Even FreeCAD has a degree of finite element kind of built in as an add-on. So in the past, you kind of had designers, or maybe not even so much in the past, but in some areas, the aerospace industry in particular, or aerospace field, you kind of have your set of designers that are working on, okay, will I be able to meet these functional requirements of getting a rocket into space? And then they throw the design over the wall, almost literally, to their neighbors for them to do the design analysis or the structural analysis, okay, and verify that it will not fail. So there's really, there's back and forth there, and if you can be the person that does this back and forth in your head a little bit, you can save your future employer time. Okay, and so being able to even see the stress and strain distributions on your CAD in the computer and be like, oh yeah, that's an equivalent stress. And I remember something that we talked about in mechanics and materials to relate that to what kind of shear stresses might be occurring. And if I change the geometry a little bit, I can reduce the shear stress, or I can change the geometry a little bit and reduce the normal stress, whatever it might be. Or, what's the easiest way is to make things bigger and thicker, right? That's often the way. It can increase the cross-sectional area, right? That also comes back to what we've been discussing, right? But what's the cost of increasing the cross-sectional area? I think the cost is mass, which is weight, right? And if you have to lift more off the ground, that's a problem. Or if you're running along the ground, it's not an aerospace application, right? And you have a heavier vehicle, that's going to require more energy, more power to be able to get the acceleration, the speeds that you want, and that's going to reduce the your mileage, per whatever fuel you're using. All right, we're moving more and more toward miles per kilowatt hour instead of miles per gallon. Okay. All right. So anyway, that was a long kind of just the tangent on why we care about what we're doing, but it is relevant to what you'll be doing in the future. And that's one of the nice things about this course, is that you can walk around and you can see many of these applications. You can look at it and you'd be like, oh yeah, that's why they made it this thick, because they didn't want it to fail. That's why they made it this shape. That's why they had this cross-sectional area. That's why they've connected these beams the way they've connected them, right? They could have used pins. They could have, but instead they're using fixed welds, right? So all these concepts do come back to this course. Okay, so the first session that we get to cover is going to be 18, which goes into quite a bit of detail in being able to figure out, okay, what are the maximum in-plane shear stresses and what are the maximum normal stresses, okay? And what you'll see is that for the maximum normal stresses, those principal stresses as we call them, we're typically going to have a sigma 1 and a sigma 2. Okay, so if it might be a little bit confusing, right? Because we talked, even in pre-pro max, right? We had sigma 1, 1, sigma 2, 2, sigma 3, 3. Those were to represent the x, y, and z directions. In this case, when we're talking about in-plane stresses, sigma 1 and sigma 2 usually refer to the principal stresses, which are the maximum, and not always, often not, in the same direction as sigma x and sigma y, as it was demonstrated here. You'll also see that when we do the absolute maximum principal stresses, absolute maximum shear stresses, okay, we care about the third dimension a little bit, and so there's going to often be a sigma 3 as well. And so sigma 1 is usually the largest, sigma 2 is usually the second one, and sigma 3 is often 0 for our cases, okay, or sigma 2. So they're interchangeable, but the point is that those three are the principal stresses, okay, principal stresses or maximum normal stresses, okay. And then the shear stresses, well, you might see something like a tau max, all right? And if it's a planar system, how many shear stresses are we dealing with just in one plane? Just one, right? So we're dealing with 2 normal stresses in one plane, but and only 1 shear stress in one plane. Yes, Michael.
It's kind of a trivial question, but it kept messing me up. Which one are they talking about when they say sigma 1 and 2? Which
those are the principal stresses, right? So those are the principal stresses.
Oh, and which one is the principal and the y? Which one's the principal and the x?
So like what we're saying here, like if you look at this diagram, okay? So you might have started with a sigma x, right, or an x direction, right, and a y direction, like in these two, okay? Or yeah, this could be the x, this could be the y, right? And then we do these transformations, right, where we rotate. So now we have a sigma x prime, right, and we have a sigma y prime, or we have an x prime direction and we have a y prime direction, okay? So now we're going one step further, and we're not saying, hey, these are just arbitrary sigma x prime, sigma y prime. We're saying, where are sigma x prime and sigma y prime? Not where, at what angle of rotation are sigma x prime and sigma y prime maximums? Okay? And that's where we say sigma 1 and sigma 2. Does that make sense?
Yeah.
And it's not just their maximums. It's actually something kind of important that I should clarify, that these are states of stress where there is no shear. Okay, there's no shear. Okay, so I guess I had to, yeah, they are going to be when you have no shear stress. Okay. Now that turns out that corresponds to a sigma 1 that's the maximum. More carefully said, okay. But these are sigma 1 and sigma 2 is when tau is now equal to 0. Because you could have a sigma 2 so sigma 1 could be less and sigma 2 could be a little bit more, All right, so I guess I should be careful, but yeah, it's the state where there's no shear stress. That's what in-plane principal stresses are getting at. And a sigma 1 should be a max. All right. Thank you for asking that clarifying question. Okay, and then the tau max, or the in-plane max shear stresses, all right, or in-plane max shear stress, that's when you're going to have a tau max, right? And so that maybe is a little bit more straightforward. That is a max, all right? And that is going to sometimes have no normal stress. So like the state of pure shear. Do you remember when we talked about torsion problems and we're like, hey, there's no normal stress on this element, right? We've now seen that for the combined loadings. We just look at what that T-app is doing and there's no normal stress on those elements. So that's pure shear. So that pure shear situation, tau max, corresponds to that calculated TC over J that we've had. In many cases that are not pure shear, what happens is you get a maximum shear stress, but there's still some normal stress. And that normal stress is going to average out. So your maximum shear stress is going to be something, and then you're going to have some other normal stresses, okay? And they don't necessarily, like, okay, so if you go, let's see where we can go. Yeah, so, well, these are situations where, okay, we can think about, all right, what is happening with the normal stresses, okay? And they could, it's actually, you have to be careful. Okay, so pure shear, all right, can be like this, all right, where you have zero and zero normal stresses, all right? Sorry, okay, hold on. Yes, you can rotate to get maximum shear stress, okay, and that angle is going to be a sigma F, or theta S, okay? And when we rotate, for example, to, let's say, this right here, which is somewhere around 20 or 30, okay, we see that we get a sigma X prime that is a value, and let's say it's around 70 megapascals, and we get a sigma Y prime that is also around 70 megapascals, okay, in this particular case. And then if we rotate another 45 degrees on the element, what we see is that we get to a state where the shear stress goes to zero, but the sigma X prime goes to a max, right? We see that. And we have a sigma Y prime that is also, okay, getting to a local minima, all right, at this location, all right? So another thing to point out here is that the offset between, say, theta P, okay, so theta P corresponds to the angle where you have the principal stresses, and theta S corresponds to the state where you have the maximum in-plane shear stresses. These are 45 degrees offset from each other. And that has profound implications when you think about what's happening in pure shear and what's happening in normal uniaxial loading, okay? Because normal uniaxial loading is what we typically do. That's a tensile test, right? You take the material and you just pull it apart. And so when you do that, you're like, oh, okay, well, I got the normal stresses in the direction. But if you're doing it for a ductile material, it actually fails because of shear. So what you can do is you can look at those materials that are ductile, and if you look at the orientation 45 degrees, either from the vertical or for the horizontal, there are lines that form, and those are shear planes where the material actually fails, okay? And that's where the maximum shear stress is happening, at 45 degrees relative to that. Okay. I'm saying a lot, there's a lot of information here, and I'm skipping over details, but this is just to give the general overview, okay, for session 18. So go ahead and spend some time on session 18, all right, and then in a little bit, I'll talk about what's going on in session 19, which has to do with what we call Mohr's circle. And Mohr's circle is kind of, well, it is a graphical method to shortcut a lot of the equations that we're using here, okay? All right, one other thing though, just for this session, and I encourage you to not reprogram the code into MATLAB or some other language, just hit Control Enter, okay? If you are working on this and want to be able to graphically calculate some of the answers to the questions that you have in this session, just pull this one open. You can look at these examples. So essentially, what I've done is I've put the stress transformation equations in here, okay, and they give you the plots. All right. So all that is necessary is to hit Control Enter, okay, on this file in Google, and hit Control Enter, all right, here. And in some cases, you know, you're just given the values for sigma x, sigma y, and tau xy, and then you can look at the resulting plots to see, okay, this is when the max, this is where I have a maximum shear stress, right? That's where I have a maximum in-plane shear stress. So, you know, I'm going to go ahead and estimate, oh, well, that's you know, maybe close to 30 or something like that, right? And so you can do some of these problems just by graphing and looking at the results, okay? And then also, okay, I've even got things that will spit out where the maximums are at the angles, right, and the stresses. So you know, this is all there for you to use to make your life easier. So just hit Control Enter, and you'll be able to do some of these problems without too much difficulty, okay? And of course, you can copy this over to your own folder or whatever you like for keeping track of these collabs. This is, you know, this is a Google Doc, essentially. Okay? All right, great. So go ahead, get started. Happy to answer questions.
I like using MATLAB because I put it myself. I actually understand what I'm doing here instead of just putting numbers in using your code.
Well, go ahead and just retype it then.
Yeah, but
In Colab.
Colab or MATLAB, it's the same thing essentially.
It is.
It's easier that way. The point is doing it myself and then get a better understanding of it like that.
I mean, I'm not going to stop you from doing it that way. I think that learning Python in today's age is extremely important.
Okay.
Extremely important. Okay.
Fair enough.
So, you know, if you're looking at, well, I think if you're looking at the future of what we're going to be doing,
Okay.
Python is going to be a useful skill to have. And they're really easy. The files are really easy to share
Yeah.
in Colab.
Yeah, the triangle's just also one triangle. But yeah, that would make a simple triangle. This is supposed to be the same slope as this. This is also supposed to be in line with this prime. So now you guys, I did not draw any lines straight as they should be. This should be like this. And like that. So now I need to see the X prime. Delta A. Which is one is delta A. You see this one.
Any questions?
Yes.
Okay, what's up?
For 16, I think it's 4.
Okay, hold on. Which one? Session 16?
So it's a complicated one.
Okay, yes.
Just kind of, I don't know what time, I've looked at it, it's like, we're working 90 degrees here, so. Around this time, right? This was just, holding this base.
Oh, 17, not 16.
Sorry,
17.
yeah, sorry.
Yeah. So you saw what I sent in the group me, right? Hello, how's it going, Owen?
Do you just want the original direct? It's PR sent to it.
X stays the same.
That's right, x becomes x prime,
Yeah.
right? And so now we rotated 90 degrees, so the y that was up, becomes coming out facing us, right?
Okay.
The z that was facing us
Now,
is now down,
okay.
and the minus y.
Okay.
So which one, so now which one are you looking at?
So how much Y would change?
Yes.
Okay.
So that's a little.
Also,
bit-
how is X,
Well,
Y?
hold on. How x prime, z prime.
So it says here's how X prime and Y prime, right? It should be Z prime, Y prime.
It should be tau x prime z prime.
Okay.
I thought I changed it. It didn't change?
This is, I mean, it's could be this old version, I don't know.
Let me see.
Because that would make more sense.
Yeah, it's tau x prime z prime.
Okay, fine.
Does it say, I am sorry, I thought I changed it yesterday.
I'm in class right now.
Oops. Okay, so let me check it. It should be tau x prime z prime.
Okay.
Yes, it should be. I'm glad you asked.
So,
It says tau x prime z prime on my version. Which version? Says this is tau x prime z prime. Whoa. Okay, have you not submitted it yet?
no.
Ah, that might be, so this is the first version. Yeah, so I updated it,
Submit it and you're starting it.
Yeah, submit and restart. The question doesn't
So,
change.
What question?
Question 4, or question 4 and 17. Yeah. Yeah, so it was a mistake. Yeah, now if we rerun,
And there we go. Okay.
okay, so you must have started it
Yes.
like
Yes.
before last,
Yes.
during last class or
Yes.
something. Okay,
Okay, there we go.
good, alright. Is that now, are we good?
So, but how do we do the top part still? So,
Okay, yeah, so let's look at it, right?
mhm.
There are a couple ways to look at this problem. Alright, so let's go over here. Okay. So we agree this is x prime, right? This is what I sent out in the
Yes.
in the group meeting, right? So this is x prime x, y is up originally, right? But now y prime's coming out, z is originally coming out, and then it becomes z prime going down,
Okay.
okay? So now the question is, we're interested in tau x prime z prime,
Mhm.
right?
Yeah.
Where is the x prime face? This one right here, right? This is the x prime face?
Mhm.
Okay. Which direction is z prime in?
It's the bottom one.
Right. Is this arrow? This is the original tau xy. Is that arrow in the positive z prime direction or the negative z prime direction? Z prime is now positive going downward.
This is negative Z prime.
Right, so this is a negative. It's the same value, the same 10 megapascals that we have, but it's now negative.
Okay.
Right? Does that make sense? Now, that's one way to do it. The other way to do this problem, okay, is actually to use the rotation matrices, okay, which we said. So the other way to do it is, okay, plug in these values, and this, you have this collab in the so if we go to session 17, for the example, right, example 17.5, right, we said, okay, we're doing an angle of 30 degrees.
Yeah.
Instead, if we want, we can do a rotation, okay, of, well, actually, we had to do, this is an RZ rotation. Okay, so no, we don't do an RZ rotation, we do a RX rotation. Okay, so this is a little bit more complicated. So you don't do the RZ one, you do the RX rotation. Okay, and you do if you do that rotation, right? So now we have our our MP dot RX, that's what we're looking with MP dot the sigma with the transpose of RX. So if you use this instead, you can get the output of a tensor, okay, for the sigma prime. And this component is complicated to look at, but this is going to be the sigma x, because it's the first one.
Okay.
This one will be sigma y, right? But it's e to the minus 31, so this is 0.
Okay.
And this is the sigma z. This is, and what do I mean? Sorry, this is the sigma z prime, I should say that. This is the sigma y prime, and this is the sigma x prime.
Okay.
This component right here is the tau x prime z prime. Okay, it's very hard to see. Let me see if this will help it a little bit.
Okay, I think that makes sense.
Right? So if we how can we make it look a little bit neater? It's maybe a little bit neater. Just move this down here, right? So this is the tensor, okay? So those are two ways to approach the problem. But the easiest, well, the fastest is to use, just use the visual method here.
Okay, yeah.
Okay.
Does
Does that make sense?
Yeah, I got it.
Thank you for asking that question. Yeah, because I did change it because I realized yesterday that I had made a mistake, and so I updated Canvas. But
yeah.
yes, okay.
Okay.
Good.
Thank you.
And in the group meeting, that would have been confusing because in the group meeting we were talking about tau x prime z prime, and you're like, oh, it doesn't say that.
Let's do assignments for 18. Wait, that's weird. How many assignments? Oh, okay. 2 assignments for session 18 are just title quizzes too.
Mm-hmm.
Look at the Canvas assignments. Two of them are mislabeled.
Which ones are mislabeled?
Canvas is session 18 Q1, then quizzes 2, and session 18 Q4.
Oh, they're okay. They're just mislabeled.
Yeah.
I can.
No big deal, but
Yeah. Okay. Let me see if I can change that for future generations. That is weird. When did that happen? So in about 5 minutes, I'll just talk a little bit about Mohr circle for everybody. Okay, so around 11:30.
I just want to.
What is that?
It's just weird.
So here.
Which one is that? It's worth 0.999 points.
What? I mean, apparently it rounds to 1, so still.
I do not know.
It's funny. Whatever.
Why would they have done that?
It's probably because it's 3 questions. Like they
Oh,
all have to be
I
equal.
see.
Oh.
30 each. Yeah, okay, there you go. That makes sense.
Oh, because I might have put in 0.3333, 0.3333, and 0.3333.
There you go.
Okay,
Great.
that's why. Thank you, Mark. I can't remember because I did it a while ago.
There we go.
You'll be okay with that.
Totally fine.
Okay.
Oh, sure.
What do you do the stress test? I get to get the. Then you have to do here.
Question.
Yes.
In this formula here, set tau max.
Yeah.
This plus tau xy squared times x.
No, that's a typo. Which slide was that on? That's on. But that's in that's
I think
in
it's 28.
18.
Yeah.
Okay.
28, 27, 29. One of those three.
Yeah. That is a typo.
Yeah.
All right, so let's take a moment to discuss Mohr's circle. Okay, this is going to be session 19, and Mohr's circle is one of the critical concepts that you'll take away from this course, and really is something universal that mechanical, civil, aerospace, what are we forgetting? Biomedical, anyone that deals with structures and materials is going to be familiar with Mohr's circle, okay? And it's, again, it's a graphical method for being able to use the stress transformation equations. And if you think about it, go all the way back to being able to do the diagrams where you have the triangles and you're performing equilibrium. Okay, so it's very, very, very useful. Okay, now the steps okay, to doing Mohr circle are outlined, okay, in the slides, okay, and you can go through and watch the derivations. Okay. But if you want, this is a pretty good slide. It's a little bit into the session in terms of how you can go about doing or making a Mohr circle. So we're going to draw the axes, the sigma and the tau, okay? And we're going to call tau positive going downward. One thing that you'll see, and I point out, is that there are different conventions. Hey George, how's it going? There are different conventions that people use for Mohr circle, and we talk about that a little bit, or I talked about that a little bit in the video. The convention that we are using is that tau is positive when it goes downward, like you see here. And so after you've drawn the axes as such, we're going to plot what we call the center of the circle, and that's the average normal stress. Okay, so you just take whatever it is, whatever your sigma x and your sigma y are, you just figure out what is the average between those two, and that becomes the center. Once you've put that average, once you put down that center, okay, then you're going to plot sigma x, tau xy. Now, what's interesting is we've decided to plot sigma x, tau xy. There's also a sigma y, okay? And the sigma y, that's a second reference point, right? That's sigma y comma minus tau xy, all right? This is the way you do it though. So we'll plot our sigma x, tau xy out here, right? And remember, tau xy is positive below the axis. And then after we've plotted it, we have to figure out the length of the radius. So we want to figure out the radius of Mohr's circle. Okay, and we do that, as you see here. And then once we've got the radius, we can figure out things like, what is the new sigma x prime associated with a degree of rotation? Okay, so for example, here I have a radius and I have some angle, and if I want to get to having my principal stresses where sigma 1 is the most and tau is equal to 0, I have to figure out what amount of rotation I have to do to get there. Okay, and that rotation, that 2 theta rotation, okay, that rotation, or the rotation on Mohr's circle, okay, is twice the rotation you have for the element itself. Okay, so remember we've been rotating our elements, our material elements by theta, all right, and we're typically defining theta as counterclockwise, positive in the counterclockwise direction. So what we're saying now is that we can create this graphical abstraction using Mohr's circle, but rotation on Mohr's circle is twice that of the actual element. This will come up and be confusing, okay? All right, so please keep in mind, watch, how you do this, whether it's, the videos that I've posted or other people who do Mohr's circle, but be aware that that angle of rotation, okay, is twice on Mohr's circle. It's in the same direction using our convention, using Hibbeler's convention, with tau going downward. The nice thing is that a counterclockwise rotation here corresponds to a counterclockwise rotation here. Okay, so, but it's twice on Mohr's circle. I don't know how many times I'm going to say twice. It's a lot of times, I guess, that I say twice. twice what it is when we rotate the element. Okay. The beautiful thing about Mohr's circle is that it clearly indicates where the principal stresses are and where the maximum in-plane shear stresses are. That is the beauty of Mohr's circle. So you guys tell me, if you look at this, knowing that first, I'm looking for a maximum in-plane shear stress. Where on this circle is the maximum in-plane shear stress? Where is tau a max? Top and bottom, right? That's the top and bottom. So instantly, we know what that value is, okay? And remember, we said when you're in the state of maximum in-plane shear stress, we have a sigma average. The sigma average, right? Look, this is sigma, this is a sigma agma, right? At the top or the bottom, that's where I have my state of maximum in-plane shear stress. If I'm here, okay, this is from maximum in-plane shear stress. If I'm here or there, okay, I now have my tau max, sorry, I have to do it the other way. I now have my sigma average, comma, tau max, right there. Here, it's also sigma average, okay, and this is minus tau max. We were talking about this before. The reference point P corresponds to sigma x tau xy, but also when you plot this out, sigma y can be related to minus tau xy. So if I draw this one out here, this is going to be the original sigma y minus tau xy. Okay. There's a lot here. Okay, there's quite a bit here, all right, to kind of settle on, but it's very useful once you get it, all right. So this is where the maximum in-plane shear stress is. Now let's talk about where the maximum normal stress is. The maximum normal stress is here, right? That's what we'll call sigma 1, comma 0. And then we have a corresponding sigma 2, which is not at its maximum, right? It's actually at a minimum here. And that has 0 shear stress. Both of those have 0 shear stress. That's the definition of principal stresses. Okay? So when you do the Mohr circle, what you'll see is that you can easily figure out where the principal stresses are, and you can easily figure out where the maximum in-plane shear stress is, okay? Because you've drawn this Mohr circle. And what's also neat is that you can, without too much difficulty, figure out how much you have to rotate to get to these different states. So this is where you start. This is like your initial state. And then to get to the maximum, or to get to principal stresses, right, I had to rotate some amount. If this were 45 degrees, or if this were 50 degrees, or 60 degrees, right, when I say this, I'm saying if this angle in here were like 60 degrees, all right, then it would correspond to a theta equals 30 degrees of rotation to get to the state of principal stresses. I rotate by a clockwise amount, right? Half. Remember the 2 theta that we were talking about? And if I'm interested in figuring out where or how much rotation I have to do, okay, to get to a state of maximum in-plane shear stress, I have to go out here. So before we said, oh, that was a rotation of 30 degrees, right? That was 60 degrees in there. So that means that this would have been, so from here to here was 60. So this would have been 30 in there, okay? And then I've got to go another 90. Okay, to get there. So I've got to go a total of 120. Okay. All right, to get all the way up there. So that would give us, no, I think I did that. I said 45, yeah, so we said we had a theta, so it should be 40, I must have done the math wrong here, but the point is, yeah, let's just say, so before we said we had this angle to get from there to there, yeah, we said this was 60 degrees, okay, we've got to go another 40, well that's, okay, actually no, that's, we have to go vertical, okay, we'll just leave it at that, I did something wrong. We have to go vertical to get all the way up here, and let's say that if that angle were 120 degrees, okay, then we'd have to go theta equals 60. This is wrong though, because you always are going to be the maximum in plane shear stress is going to be 45 degrees relative to the principal stresses. Okay, this angle from here to here is going to be 45 degrees. Oh, that's why I did it wrong, because I was going to this state. Yeah. Before, what we said is, okay, yeah, we were saying if this were from here to here, we were saying that this was 60 degrees. And then from here to here, we've got to go another 90 degrees. Okay, 90 plus 60 is 150. So theta S would have been 150. To theta S, so theta S would have been 75 degrees. Okay, clockwise. The alternative, okay, to get there is to go going clockwise. So if I want to go clockwise, we just said a second ago that we had to go 60 degrees between here and here. So if we go clockwise 30 degrees, okay, that will get us to the state of principal stress as well, right here. And so a state of maximum in-plane shear stress, oh my goodness, is also, can also be said to be minus 15. Half 2 theta is 30 or minus 30 degrees, and so theta S can also be minus 15 degrees. Yes?
Is the center of the circle always on the sigma axis?
The center of the circle is always on the horizontal sigma axis. Yes. Okay. Yes.
What if you have pure shear and there's not, like the center is shear?
Okay. Good. Let's come out here. Oh. Let's come out here. Now I'm liking these questions. Pure shear. Okay. So what does that mean? That means that sigma x equals sigma y is equal to 0. And we have some value.
Yeah.
Okay, tau. Okay. Well, first thing I do is I draw my two axes. And now you're telling me that pure shear, right, I have sigma x equals sigma y equals 0. Well, what's the sigma average? 0. So the center is still on the sigma axis, but it's at the origin. Okay. Now the next thing I was supposed to plot, right, is this sigma x, comma, tau xy, right? That's what I'm supposed to plot. Well, tau xy would be just the tau, so that's going to be down here. Okay, so that's the tau. Now I can draw the R, right? We talked about drawing the R, so I can draw the R. Okay, so what is R equal to? R is just going to be equal to tau. Okay, and then I can draw my Mohr circle. Just like that. So it's centered at the origin. Okay, what is the maximum in-plane shear stress? Well, it's tau, it's pure shear. What are the principal stresses? Sigma 1, sigma 2. Well, look, it's just R. I rotate up to here. Sigma 1 is equal to R. Sigma 2 is equal to minus R. Okay? And that's, again, so the theta p that's necessary to get to the principal stresses is 45 degrees, right? Or 2 theta p is equal to 90 degrees. And that's counterclockwise. This is a good question to ask Carlos because this corresponds to a situation, right, where you have a cylinder that might be having some applied torque to it, right? And then I know, right, that the maximum, you know, if I'm looking at an element here, I know that this element is being twisted like this, okay? And I know that my shear stress is going to be just Tc over J, right? But now I can figure out what the equivalent normal stress is, right? Or would be, okay? And if I want principal stresses, or, you know, this is actually equivalent normal stresses and shear stress, right? Because if I go to other locations, say I'm here and here, right? I have both normal and shear stress, right? It's just, the shear stresses don't go away until I get to the state of principal stress. Okay. So I can figure out what the equivalent principal stresses are as well. And that's where I have my sigma 1 is equal to R, and my sigma 2 is equal to minus R. Okay? So that this is the pure shear, the state of pure shear is very important. Okay? And there's also the state of uniaxial loading, which is very important. Okay? And I'll let you get into the notes on that, right? Because those are kind of two basic states where you can have pure shear and you can have pure uniaxial loading. And uniaxial loading, okay, sure, I'll do it because why not? Uniaxial loading, and we cover this in the videos, is an interesting case, right? Because we do our tensile testing in this scenario. So if I have some force being applied to pull apart this sample, right? And I know that I've got some, you know, cross-sectional area. It's easier just to rewrite it, I guess. Like that. I know that if I have this cross-sectional area A, right, that sigma is just going to be equal to F over A. And in this case, right, I could say, well, let's just call it sigma x. We'll call this the x direction. Okay, and we'll call this one the y direction. Okay, so sigma x is equal to this f over a. Sigma y is equal to 0. We can also say that sigma z is equal to 0, but let's just look at a plane, right? What is the shear stress in this situation? That's also going to be equal to 0. Okay, so those are equal to 0. What does Mohr's circle look like? So yeah, I could go through the transformation equations. I could go through my triangular slice and do all the equilibrium, but it's simpler just to look at Mohr's circle, right? So again, I draw my axes, and where's the average? Where's the center of the circle? The center of the circle, right? The center is at sigma average, comma 0. That's where the center is. So it's actually going to be at sigma x over 2, right? Comma 0. So this is, it's going to, let's just put it here, for example. So we'll put the center right there. Where is the sigma x going to be? Well, I'm going to plot that, right? We say the point P is going to be sigma x tau xy. Well, this is just sigma x, or the f over a, if we want, however we want to do it, f over a, comma 0, because the tau xy is 0. We said that already. So that puts us out here. Use a different color. Okay. So this is sigma x, comma 0. This one over here is the center. That's at sigma average, comma 0. I can figure out what the radius is right here. That's r. Okay. The radius is a little bit trickier here because the radius is actually not that much trickier. It's actually sigma x minus sigma average. Okay. And now I can draw more circle. So I draw the circle, and I know it's going to hit the origin there. Looks like that, because r, okay, well, okay, so yes, it's sigma x minus sigma average. This is also equal to sigma average, right? Because sigma average is half of sigma x, right? It all works out, right? So, I mean, just so everyone sees that, right? This is sigma x minus sigma x over 2, right? This is going to be sigma x over 2. So where is the state of principal stress? We're in the state of principal stresses. Okay, look. This is sigma 1 is equal to sigma x in this case. And sigma 2 is equal to 0. So uniaxial loading is a state, or the normal, how we normally describe it. We normally describe it in terms of its principal stresses. Where is the maximum in-plane shear stress? This is the question, right? So now we can figure out, especially for a ductile material which fails in shear, we can figure out what the equivalent shear stress is, okay, by moving to the top and the bottom. Right? In this scenario, what do we get? Our maximum in-plane shear stress is going to be sigma average for the x component, comma, we need a shear stress. This would be minus r, okay, if you will, because it's negative going up, and this one down here is going to be sigma average R. Okay, so this right here, the tau max in plane, okay, this is given by R. That's it. And R is equal to sigma x over 2. So, do you remember in the last exam, there was a question on question number 3, it said, here's a shear stress, shear strain plot. And you remember what we said? We said one approximation to make is that the shear stress, the shear yield stress, or the shear yield strain is half of SY, of half of the tensile yield strength. That comes from this math. Look at this. You see that? What we're saying is, let's say you calculate, or let's measure better said, SY. What is the equivalent shear strength of the material? So this is the tensile strength, right? How much shear can we handle? If I take the same material and I put it in a pure shear situation, how much shear can it handle?
Twice of the shear stress.
It's going to be half of the tensile, right? It's going to be, this is the max. Let's say that this SY is a normal stress. Okay? So let's measure SY. SY is the maximum uniaxial normal stress I can handle. Right? So that would be my maximum sigma x. Right? That'd be out here. So now the question is, what is my maximum shear strength that I can handle? Well, I have to go and look at what the maximum shear I can handle is, and it's where I have maximum in-plane shear stress. So the maximum in-plane, the maximum shear I can handle okay, so sometimes we say SSY for the shear yield strength. That's going to be equal to this tau max, the R, which is equal to 1/2 SY. All right? Because look, remember I had sigma x out here, and then I said I could only get to a tau of sigma average. So this is just by using Mohr's circle in these transformations, we're able to figure out some of these relationships between what you would expect for the case of pure shear when I've tested a material in uniaxial loading. Okay. All right. I'll let you all keep working. But if you have questions, happy to answer them. So Mohr's circle is extremely powerful for these types of graphical interpretations of what's happening as we rotate an element. And notice, right, going from this state to this state, the angle is 2 theta equals 90 degrees. So it's a rotation of the element of 45 degrees. So if I took an element in here, right, so I have like my little element, okay, and I've calculated out, you know, what the loading is, and then I take another element and I rotate it 45 degrees, okay, that will have a different state of stress, right? It will have a state of stress where I have shear now at its maximum, and I also have my sigma average, which is half. All right, we'll cover this in more detail when we do failure criteria as well. But I'm glad you asked about pure shear, because that's a very important case, and as is uniaxial loading. Okay, so there are a couple ways to do it. Plotting it is the easiest, right? But if you look at kind of what we'll put out there, to calculate the maximum shear stress, you can take the derivative of the shear stress transformation equation and set that equal to 0. Okay, so that's in the if you're looking for the maximum in plane shear stress, set that equal to 0, and then you can figure it out. Does that make sense? Okay, good question. Good question. It's actually on the slides for you too. So later on, if you're looking, so you're talking about max plane principal stresses, right? So in that case, you take the derivative of the sigma x prime, right? And then we have these expressions for sigma 1, sigma 2. And then also, right, for the maximum in plane shear stress, you take the derivative with respect to that, and you count x. As you're pointing out, there's a typo there. So let's fix that. There should be no x there. This is, all right, so you don't have to read the right.
Yeah, I got enough.
Okay, all right. Well, I mean, what I was hoping is that you just use the collab to get a feel for it, right? And you just look at the plot, right? And you're like, oh yeah, it's about there. And the collab also spits out those, it goes through, it searches the arrays of the betas and the taus and the sigmas to figure out, and then you can, and it finds where their maps are in. To each their own. I'm just gonna stop this for a second while I take care of something. Yeah, so I think the typo, there was a typo on this slide right here. Have you found any other typos? I'm gonna I'm just gonna upload this. Yeah.
Professor,
Yes.
in all your equations, you use tau xy, but can we also use like other directions?
Okay, what do you mean by that?
Or like, because in the equations you have like tau xy, right? Because that's tau in the x face in the y direction.
Yes.
So could you like have it like in the x face in the z direction?
Beautiful question. Yes, absolutely. These equations are only good for one plane though. Okay? On Monday, we're going to talk about how to deal with the 3D aspect of the problem. But we're typically only working in one plane. Okay? Except when we need the absolute maximum shear stress. When we need the absolute maximum shear stress, we use Mohr circle again. But there's also, you can solve, there's a complicated equation, which we won't derive, that that you can use when you find some roots to figure out what sigma 1, sigma 2, and sigma 3 are in 3 dimensions. Good question, good question. So that'll be covered in session 20, and that's the last thing we cover right before the exam. Good, I'm glad you asked that question.
Question.
Yes.
I'm pretty sure I'm getting this right. Correct me if I'm wrong.
Okay, hold on just one second. Let me just get this one thing. Okay, what's the question?
So for the radius, the square root of the tau x y squared plus the center of 2 squared, correct?
Say the
That's
radius?
radius, correct?
So again, are you in more circle?
Yes.
I would do it graphically, alright, but this
it's-
equation,
this-
yes.
this is basically the graph, generalized graph essentially. Radius, the center, plus center root 2, plus that square, get that line, right? That should be good.
This is your point, right?
Yes.
Yeah, so you're figuring out what is your tau, you're figuring out the hypotenuse of this, right?
Yes.
So it should be, yes, the tau xy squared, right, plus, it's actually a little bit, from this point, it's this minus this. Okay,
Minus being,
so it's going to be, because you had to have the average, so it's,
Right.
it's the sigma x minus the sigma average squared. Then take the square root of that. That will give you the radius.
so sigma x minus sigma average squared.
Yes. So it's the square root of tau xy squared
Okay.
plus the sigma x minus the sigma average squared.
You need sigma y, I guess in this case, really. Sigma y for this guy, really.
Sure. I don't know which one that is, but yes.
That means sigma x, okay, yeah.
Yes. Either one will do it, but it's going to you need either the sigma y or the sigma x minus the average.
Okay, thank you.
Sure. There was a typo here, there was an extra X, that's been corrected now. Any questions? I hear a sigh. Any issues?
So there's just one stress that he just, this, right?
If there is one normal stress, then you have a situation where you have, yes, that was what we
Okay.
just covered, that's the uniaxial loading
Okay,
case. Yeah.
Maybe they didn't make it today.
It's too bad.
You woke up very late. Like 20 minutes.
Okay, yeah. I understand.
The weather was not helping.
No, it's not. I thought I was gonna get rained on today, but I think,
It's gonna rain later on.
yeah,
Like this whole week is all rain.
yeah.
And small boys graduation. So tomorrow it's gonna be so bad.
What type of graduation?
High school. It's good.
Nice.
Yeah.
Yeah, I had kind of, my daughter had her 8th grade graduation last night.
So,
What's up?
just
So if you can figure out what that height is, you already know what the radius is, and so that's how you figure out the angle. Because it's gonna be then sine of theta is equal to this height divided by r. The alternative is to figure out where it is in the sigma direction, right? So if you know that this, well, I don't know which one's sigma x and sigma y, it depends on what you started with, right? But if you know what the sigma value is here, right, then you can figure out the sigma value, right, so it corresponds to about there minus the average, right? That will be so cosine of theta will be equal to this sigma minus sigma average divided by r.
And then that divided by 2 again.
Right, because that's the 2 theta, sorry, yes, that's absolutely right. That's good. Okay? Good question. Do you mind, I'm just gonna point out something that Michael brought up. And that is, let's say you're in a situation where you got some type of Mohr circle. Okay, something arbitrary like this. And let's just say that, you've got a sigma x and a tau xy here, and you're trying to figure out what the angle is in here. Okay, you've got a 2 theta. This is really poorly drawn. Okay, and actually this is even more poorly drawn because this is minus tau x. Well, it could be your tau. If your tau xy is negative, right? It's fine. All right, so this is in real number, it's a negative value. It's less than 0. But anyway, what you do is you use the property of right triangles, right, to figure out what this 2 theta is, and you have 2 options. One is, you know what the sigma average is as well. One is you say that, well, we actually have 3 options. Okay, one is to say, all right, I'm going to say cosine of 2 theta is equal to what? It's going to be the sigma x minus the sigma av over r. Another option is sine of 2 theta is this tau xy, we'll say absolute magnitude of the tau xy over r. And then you could do the tangent. You probably don't want to do that, but you could also do tangent of 2 theta. I mean, you could, if you don't want to calculate what r is, I guess you could do it that way. It would be tau xy over sigma x minus sigma average. So those are kind of your alternatives. Okay, well, thank you all for coming. Thank you for your questions. It's good. It's good when we can discuss the problems. I appreciate that. And I hope you all have a good weekend. As a reminder, there are 2 sessions two sets of questions for 2 sessions due on Monday. Tuesday we'll cover the last topic, or on Monday we'll cover the last topic for the exam. Those questions will be due Tuesday. Then Wednesday is the exam. And then what we cover on Tuesday will be due on Thursday. All right, thanks. Have a good one.
What we cover on Tuesday is going to be on the Wednesday exam?
No, what we cover on Monday, the last topic, is on the Wednesday exam. So if you want to really get ahead, you can plow through everything. The problems are all there, and try to get that done over the weekend. And then you have more time to study.
Have a good one.
All right, you too.